Equation of motion for viscous damping. Damping means the presence of frictional forces in the structure, which transforms the mechanical energy of a system into other forms of energy such as heat. You can take an example of the dampers of the motor car. You have observed when the car travel on the road, if there is holes on present on the road, then if the dampers are not present, then there very painful shock will hit to the person. Okay, even may some danger, injury the driver may face. So the shock absorber absorbs the energy, okay, the mechanical energy, and transform into the heat energy. Then this heat energy is dissipated in the form of liquid where cooling agents are present. Okay, so that's how damping works. So now in this topic I will discuss the damping in the structures, in the concrete structures, in the steel structures, in the buildings. If damping is completely absent in any ideal system, a structure once excited will oscillate indefinitely with constant amplitude and at its frequency. For example, the pendulum. If there is no frictional forces present in the pendulum, then the pendulum will oscillate indefinitely and infinitely uh, without stopping. Okay, so this is just the first law of Newton. A viscous damper model considers damping behavior to be similar to piston moving a viscous fluid. This is the car example. The symbol and the demonstration of the damping in the model is just like same as the viscous damper of a car. The viscous damping forces produced are proportional to the velocity of the piston. That is, we have already discussed in the previous lecture that damping is directly proportional to the velocity. However, the actual damping in a structure, means in a building structure, may result from looseness of joints, means damping can be result from looseness of joint, dry friction between components, between beam columns. Okay, material damping I will discuss one by one each, and structural damping, that is the overall of the structure, general term for all type of structure of damping in a structure, and many other complex causes that would lead to non-linear behavior of the structure. I will come to this point later. First I will show you this video. Here is a simple structure, okay, with its own properties, and this structure is with the external dampers. Okay, you can observe the behavior. If the occupants in this building will feel less shocks and the vibrations in this building, the people face much heavy vibrations and shocks. Okay, so in this building external dampers are applied, but we cannot say this building do not have its damping. This building also have its damping. Okay, like for example the material damping, like the friction between the joints. Okay, if any joint is loose, then from looseness of joint. Okay, so damping is present, but the damping is too less. Okay, for example, normally in buildings we take 5%, but by providing dampers we can increase up to 30%, 40%. Okay, so now I will go back to my previous point. However, the actual damping in a structure may result from looseness of joint. Second, dry friction between components, also called column damping. Third one is the material damping. Okay, material damping, the damping of, for example, concrete material, steel material. Okay, so that depends upon the material. Structural damping is the damping of the overall structure, a general term for all type of damping in a structure. and many other complex causes that would lead to non-linear behavior of the structure. Another damping behavior comes from the opening and closing of micro cracks in the structure. Okay, that is also the damping. Structural damping is proportional to the displacement. Okay, uh, if there is more displacement, then the damping will be more. But in phase with velocity of harmonically oscillating system, usually here it is directly proportional to the displacement, but in the calculations we use velocity. Why? Usually an attempt is made to express all types of damping together in terms of equivalent viscous damping. Okay, we use the structural damping with respect to velocity, and we term the damping as equivalent viscous damping. Okay, here that is Fd is equal to C u dash. U dash is the velocity. In case of viscous dampers of figure 10.3.3, here you can see the wheel model. Okay, here is a mass and here is a stiffness, here is a damping. Okay, see, the damping model is just like the damper of moving car, or the motor car. The damping force produced is directly proportional to the magnitude of velocity and opposite in direction to the motion. Okay, and that is opposite to the direction to the motion. When we apply the load and left the building, then left the mass, then it tries to bring its original position. We'll apply the load in this direction. This also tries to bring back to the original position. These all points I have discussed. Like, there are three resistant forces act when we apply the force in this direction. They try to bring back the model to its original position. One is the inertia, mass of the body. Second is the stiffness of the model, that is a elastic restoring force. And third one is the damping. Okay, for equilibrium of mass, that is the basic dynamic equation, m u double dash double dot, that is x inertia, inertial force, damping force, elastic restoring force. Okay, in this model also, when applied the force, then the force removed, body starts moving its under own weight. Okay, so that's why Ft is equal to 0. The constant of proportionality is known as viscous damping coefficient, that is C, denoted by C and having a units of Newton second per millimeter. Okay, for equilibrium of mass. The exponential function u is equal to constant C e power pt satisfy the differential equation. This equation satisfied by this solution. Okay, now I am taking the derivative of u dash c. C is the constant that will outside, and derivative of e power pt. The derivative of e power pt will be p into e power pt. Why? When we take the derivative of exponential function e power pt, then the e power pt will come outside, and the derivative of upper function with respect to t, then t by t will be cancelled out, only the p will remain, so that's why p will come out. Okay, then take the second time derivative. Okay, then again c will remain same, p again will come out, then the second derivative is c is equal to acceleration is equal to constant c p square e power pt. From the differential, I will also show what is p. From the differential equation we get, now I am putting the value of u dash and u dot and u double dot. Okay, you can see m cp square ept plus cp small c capital constant c p e power pt, okay, plus k C constant e power pt is equal to 0. In this whole equation, C is constant. Okay, also e power pt is constant. I am taking common, and then on other side taking divided by 0, that is become 0. So rest of the equation is mp square plus cp plus k. Now I will divide this equation by m. Okay, but by dividing m, now you can see this is just like the quadratic equation. Okay, ax square plus bx plus c. Okay, this equation is called the characteristic equation of the system. The two roots of this characteristic equation are, by applying the quadratic equation, we get this minus c over 2m plus minus under root c over 2m whole square minus km. You can put the value of a, b, c in the quadratic equation. Hence the general solution of the equation is given by the superposition of two possible solutions, and is given by and is given below. This is the general solution of the equation of the basic differential equation. This is the general solution for that. Okay, I will put the values for these. How we can use this, where C1 and C2 are the constants of integration to be determined from the initial conditions. Initial condition means when we start the vibration, or before starting the force on the before starting the applying of force on a model on a M, then at that time the initial condition. Okay, the following three distinct cases of solution P1 and P2 are possible depending upon whether the quantity under the radical in the characteristic equation is 0. Okay, in this under this and square root, there are three number of possible solutions. Okay, here, if under the square root, okay, if under the square root c over 2m whole square minus k over m equal to 0, then this will be equal at this condition, this will be called critical damped system. Okay, if c over 2m is greater than k over m, then the answer under the under root will become positive. This is called our damped system. Okay, real roots. If our c over 2m whole square, if our c over 2m our whole square less than k over m, then that is called under damped system. I will explain what is critical dam, over dam, and under dam. Okay, see in this video. Okay, what is under dam, critical dam, and over dam? I will also explain. You can see the magnet. Okay, here applied the force up till magnitude 20 millimeter and left the pendulum. Okay, this is a magnet, and this board is also magnetized. Now the board is away. Okay, now this mass is also magnet, and the board is also magnetized. This will face the hindrance, so it take less time to stop. Okay, that will act as a damping. Now you can see, after displacing, it will take some oscillations and stop. Okay, that is under damp. If any structure, okay, here again, that is under damp. Okay, that is critically damp. Okay, yeah. Body just comes its original position. Now it is taking more time, you can see, to come its the original position. That is the over damp condition. Damping is much more. Okay, so now here is under damp. Okay, here you can see just after displacing comes its original position, that is critically damp. After that it comes but with some time. Okay, so that are over dam, over dam, over dam. So that is the basic difference between the under dam, critically dam, and over dam. These are three cases. Okay, what is the basically there are different models, varieties or cars available in the market, with different Honda, Suzuki, many brands. Okay, uh, one brand is also Mercedes. Okay, why it basically that model has high its prices because it has high functions. Okay, their damping behavior is so good that even when it passes through any hole of on the road, it do not feel any shocks and observer to the driver. So that is the good phenomena of the damping provided in that structure. Here is the vibration demonstration. Here this dark line, that is the under damped system. Okay, when the body displays its after vibration, it comes to its original position. Okay, again with the increase in damping, the body come its original position. Okay, when the body displays and come its original position, just its original position, that is called critical damp. Okay, when it takes more time, that is over damp. Okay, so that is the over damp, under damp, and critical damp behavior.